好，感谢那个李老师他精彩的报告。因为时间关系的话，因为后台好像刚才那个科研云是不是断了？但我问一个比较小的问题，因为我是这个领域的外行，我看你做了很多就是关于 ITO， 包括它多道宽度的这个调节，在你做的这些器件当中，就是未来最有可能大规模应用的是哪一类？
最有可能大规模应用的话，就是目前的那种作为硅集成电路的一个BOL 的应用，就是在后端工艺上给它进行集成，然后在驱动电路当中对它进行使用。
好，行，那因为时间的这个关系的话，我们那个今天的报告还有提问环节就到这儿。如果就是有后台的一些老师和学生，如果有什么问题的话，可以给李老师发邮件，然后再深入的进行讨论。再次感谢李老师精彩的报告。
好，谢谢。
好，谢谢。那么我们下面的一个的报告人是来自于芝加哥大学的刘冲老师。刘冲的话是在复旦大学获得了这个本科，然后呢是在这个斯坦福的崔毅课题组获得的博士学位，然后随后呢是在那个 Steven 朱的课题组做了 postdoc， 然后刚刚入职这个18年入职这个芝加哥大学，获得这个助理教授的职位。那么我们下面呢就是欢迎刘老师精彩的报告。
好。
Okay, thanks very much for the invitation, and it's my great pleasure to be here today to share some of our most recent work in our group that works on material design for applications to supply the water, clean water, and also supply the critical energy resources. So first, the motivation of our research is because we are all living in this society that we know we have a climate change. And if you look at this figure, it tells you that if you do nothing in a century, then our ambient temperature increase would be about 4 degrees C. The 4 degrees C to you might not be a lot. You feel a daytime, nighttime temperature difference that's a lot more than 4 degrees C. But to a whole climate, 4 degrees C is a lot. And we are trying to develop a lot of critical technologies to mitigate the CO2, emission. One of the ways we are thinking about the problem is that we want to look at, because the current majority of the fuel that's used for producing the electricity is still the fossil fuel based, is still fossil fuel. And we want to know whether we can make everything more energy efficient to reduce the consumption of the fossil fuel. So if you look at the energy consumptions, you look at all these different sectors, you see mainly it's grouped into 4 categories. Like it's used by residents, it's used by transportation, it's used by industry, which counts for the majority of the energy use, 32%. And in all, always overlooked is the separation process. So this process actually is taking more than 50% of the total energy consumption in the industry. And why is that? Because this separation process to produce a lot of the critical materials or molecules are relying on energy process in the same phase. For example, you keep everything in the liquid, but you create a membrane there. And because of the membrane property, you are able to separate A and B if that happens. And that will greatly reduce the energy consumption in the industrial sector and save 90% of the energy for all the separation processes. So for membrane, it's well known that membrane has this selectivity and permeability trade-off. If you want to separate molecule A from B and you want a high selectivity, so usually what happens is that you would end up by providing a high selectivity but reducing your permeability. And at the same time, if you want to increase the productivity, meaning that you increase the flux, and what happens is that your selectivity is sacrificed. So whenever there's a new material developed, and there will be a jump of this upper borderline. So this tells us the breakthroughs in membrane to both have a high selectivity and high permeability. It relies on the materials innovation. So in our group, we look at different kinds of materials that's not polymer based, which is materials would bring in new opportunities. So let's first take a look at the length scale we are dealing with in terms of separation. So for example, if you want to separate water molecules from the ions, and these are really tiny things, water molecule is on the order of 2.7 Armstrong, and hydrated ions are 3 to 5 Armstrong. So you are talking about only a difference in 1, 2, or 3 Armstrong. So you have to have the right tool, the material with the right size to deal with the separation. So we are looking at the 2D material class. So this class of material has a very interesting layer spacing that's exactly on the right scale. So if you look at, for example, graphite, the center carbon to carbon distance is 3.4 Armstrong. And moly sulfide, this class of transition metal cauchenide, the center moly to moly distance is 6 Armstrong. So even they do show they have a repeating unit of 6 Armstrong, but actually the end sulfur to sulfur distance is really tiny, meaning there's no free volume in this material. So in their bulk form, nothing can just transport through this channel. So if we want to utilize this 2D channel for transport, for separation, we have to have ways to open up a little bit the channel to make it fit. For a long time, it's about a decade, and people have studied the confinement of carbon nanotube and how that would allow water to transport. So in this study, people have shown that if you give water a 1D confinement, actually water can transport much faster than in their bulk form. This is because the water are closely packed as a kind of like a semi-solid, and they are just going through the channel fast without rotating a lot. They're hydrogen bonds, so they don't have much interactions with the walls of the carbon nanotube. So we want to see in this 2D channel, you also have a Z dimension of confinement. We pick the 2D materials. So the first thing we do here is to make a membrane out of the 2D material to be able to test the separation and transport property. So the membrane we picked is to use hundreds or thousands of these 2D channels and to laminate them together to assemble them into a microscopic membrane. In this case, you have to start with the bulk form of moly sulfide and you exfoliate them into single individual layers. You restack them back and into this microscopic films, and that's the membrane. And because of the nature of this solution process and the membrane, the membranes when it's processed is wet, and the 2D like the moly sulfide layer to each other have a lot of water in between them when they are firstly made. But this water layers are too wide, it doesn't have the capability of separating anything because of the size. So you have to decrease the water numbers in there and to a sweet spot where is the limit you can decrease to, but you don't want to go into the region where it's totally dried. Because if it's totally dried, the molysulfide will just restack to a bulk form of the material that it doesn't allow anything to come in. So this is the critical point. You want to create a layer spacing of a sweet spot. If you are talking about one channel, that's fine. If you are talking about millions of channels, but of the identical size or shape, it's fine. But in our case, the membranes, when it's made, there are a lot of heterogeneities in the membrane, meaning that a lot of the places you have a lot of water and a lot of the places you have less water. And when you are drying something very heterogeneous, these mesoporous scale features doesn't allow a uniform creation of the 2D channel. So you will easily see from this SEM image that you have a lot of these big channels. So that will be a point where you lose your selectivity. But if you dry up the membrane, you want to decrease the big water pocket, you keep drying up the membrane. What happens is that you will be creating a lot of the dead ends in this membrane. So from these microporous scale features, the XRD shows you that the wet layered spacing, the sweet spot spacing, is 1.2 nanometer. But if you just decrease all the water away and then it go back to its bulk crystal lattice spacing, which is 6.2 Armstrong. And you can also see this in the cross-section TEM of the membrane. So this tells you that the pristine molysulfide actually is not a good or sweet material for you to work with for membranes. And what we thought about for the solution in this case is that we want to put a permanent spacer on top of the surface of the molysulfide. And definitely this way you can not only solve the issue of restacking, and also it provides you a tuning knob for you to tune the surface chemistry. Then you can really study how the surface chemistry is affecting the transport of water and ions. And you can see from after the functionalization of the small molecule there, and when you dry up the membrane, even though there's no water in between the layers, and then you got a layer spacing that's much wider than the pristine bulk form, which is 3 Armstrong or even larger, wider than the original lattice spacing. And you can also see that from the TM, cross-section TM. So now is the time for us to really measure the performance of these membranes. So let's first look at the curve, the black curve here, which is the pristine molysulfide. As I mentioned, so the molysulfide membrane, when it's made, it has a lot of this big water pocket, wide channels. So when that's the case, when these channels are percolating and you don't have a great rejection to salt because you have a leak in the membrane. And when you are trying to sealing up this water pocket and the 2D channel properties start to show up, and you do get a very high rejection of the sodium sulfate salt we tested here. But what's disappointing is that because of the drying process, you are actually sealing up a lot of the channels and they just become a dead end, permanently restacked onto each other. And that's not what we want. But after the functionalization, we pick the acetate molecule here, which can deprotonate and carries a negative charge in water. And that membrane can easily be re-wetted and be rehydrated. So you do see, like, as you dry up the membrane, it starts to show the 2D channel features that it has a good selectivity to water. But at the same time, you don't lose much of the flux of water, and you see a good membrane because you see a balance, the selectivity and the permeability. And at the end, we can just totally dry the membrane and rehydrate the membrane, and you have the highest rejection and flux at the same time. And we also showed a clear size cutoff of a big molecule dye. Then the critical thing for us in this work is we want to see how we understand the way the molecular spacer is playing here, like how you choose this molecular spacer. So actually, it is that whenever you already determined what kind of functional group you want to put into this channel, your channel width is determined because the molecules you put into there has an affinity to water. And it's not the molecule size that's determining the wetting state interlayer spacing. It's the molecule, the interaction between the molecule to water that will determine whether you would prefer one layer of water in this channel, two layers of water in this channel, or three layers of water in this channel. So you have this discrete energy wells, and each case for different molecule, your global energy minimum is at a different place. And some membrane would prefer two layers of water, and some of them would prefer one layer. And that shows you that, like, even you have, say, we look at this figure. So we know that for the carbon nanotube case, when you have a carbon surface, it doesn't carry any charge, and it has little interactions with the water molecule. And for this case, we choose the acetate. It carries a negative charge. It does have a strong interaction with the water molecule. And in the simulation, it shows that it does intrinsically have a slowest water transport property. But because its energy well, global energy well, is at a two-layer water spacing, so it does allow a higher diffusivity of water because the channel width is wider. So at the end, we through this work, we developed a platform for us to keep continuing study water transport in the confined 2D channel as well as other small molecule separation. So now I want to switch topic a little bit and to talk about another effort in our group. So to support a sustainable future, you want to supply the raw materials. So there are a lot of critical elements that are important for renewable technologies or a lot of other technologies for the future, like wind, turbine, solar, and batteries. And not every element are born equal, meaning some of them are more than the others on Earth. So we do have a security issue of the supply of some critical element. So the one thing we have for the current mining industry is that it's causing too much pollution to the environment. And if we want to keep supplying the critical element with an increased production, we have to find out a new way to do it more in a green way or in a more sustainable way. And one gigantic source of all these critical minerals is the sea, actually. So the sea contains many of dissolved ions, and the majority of the ions are like a sodium, magnesium, but there are ions that exist in a small amount, small concentration in the sea, like lithium or uranium. So those are critical elements. If you consider the total amount of seawater, they are having a gigantic reserves of lithium, billion tons, which is much higher than what we have on the land. If you compare it, that's only 50 million tons. So you have thousands of times more lithium in the sea. The challenge of extracting lithium from the sea is that you have to deal with the dilute concentration as well as the competition from the other ions. So sodium is a critical competitor to lithium because they are similar, but sodium is just a little bit larger. The way we try to develop is we want to see whether a electrochemical platform can help us to extract lithium. And we want to see the selectivity of an electrochemical intercalation reaction, meaning that you want to see whether a lithium or a sodium is more preferred in a confined structure in a crystal. So intrinsically, this intercalation reaction can give you selectivity because you have different bonding strengths of lithium to oxygen comparing to sodium to oxygen. And also, lithium is much smaller and it has a lower migration energy barrier. So how are you going to do this? So you're going to have a crystal material that's the host structure, and you want to do intercalation. And you first empty the crystal material to have some vacancies or storage sites. And then you put it into the complex environment and you do intercalation. You let the material to work on the selectivity and hope that you extract all the lithium out of the solution. And then you can recover the material and do a reverse electrochemical reaction to reject the lithium into a fresh solution to recover it. So now the question becomes, what kind of material are good for lithium extraction? So the first thing we can look at is the lithium to sodium intercalation potential difference. So this is a rich database because of the gigantic amount of work done by the battery field. So you can look at different kind or categories of material, and you look at the lithium intercalation potential, sodium intercalation potential in their pure phase. And the higher the difference would allow you to compensate more of the concentration difference. So you want a big difference in their intercalation potential. By looking at that, we determined we will work on the 1D olivine structure and 2D layered oxide material. So the first work we did is actually it follows pretty well the trend predicted by the intercalation voltage, because we do see that if you look at the lithium iron phosphate intercalation potential, it can tolerate 3 or barely 4 order of magnitude difference in their concentration. And as well, you have an add up of a benefit of the migration energy barrier energy difference. And so intrinsically, this material has a good selectivity to lithium. You want to decrease your over potential to let the thermodynamics to play the role for the selectivity. But in the electrochemical process, we all know that if you run the current, the faster you run the current, the higher your over potential would be. So that over potential will balance everything, meaning that at some point, if your over potential is high enough, then sodium wouldn't have enough energy to overcome its migration barrier and then to diffuse through the material and compete with lithium. So in this work, what we do is we try to select different kind of intercalation patterns.
刘老师你好，我稍微打断一下，就是可以稍微控制一下时间。
Oh, sorry. I'll be fast. Okay. So the key is that we select a method that can decrease the over potential, and then you can gain the lithium selectivity as well as the long-term stability. And then the next, I will just briefly talk about this. So this other type of material is more complicated, that when you have lithium sodium interaction and all this whole thing doesn't hold, so you have to put them into a different system to analyze their interaction. And this is our newest work, and we do observe the strong sodium interaction with the lithium is that whenever you create a vacancy in the host layer oxide structure and you put it into a sodium rich solution, and there will be automatic ion exchange happening. And the ion exchange happens in a way that is not a simple sodium ion replace the lithium ion in its original place, but a forced phase separation in this case, that when sodium comes in, it squeezes all the lithium ions into a corner that it forms a phase without any vacancy. And all the vacancies is given into the sodium phase, so they have a phase separation. And then we did like a pretty detailed like characterization to see in one particle where are the sodium, to identify critical features for this ion exchange. And this material does show a good lithium selectivity in a complex lithium-sodium environment. So with that, I want to acknowledge all my students who did the work, and also my all the amazing collaborators and the funding source. Thank you.
好，非常感谢那个刘老师的这个报告。因为时间的关系，已经比较晚了，但是有一个问题，就是一个很简单的问题，有那个观众问，就是关于锂空气电池，它的能量密度最高可以达到多少？要不刘老师您简短的回答一下。
这个锂空气电池的问题是不是问史菲菲老师？因为我们不做锂空气电池。
对，刚才后台把这个问题给我的时候，我也有这样的一个疑惑。好吧，那就先把这个问题留给菲菲老师吧，因为时间的关系。那后面就是观众如果还想再和刘老师沟通的话，可以通过邮件啊，然后跟刘老师进行一些沟通。好，谢谢，
谢谢。
然后我们下一个那个报告人是来自于复旦大学材料系的赵杰老师。他是博士生导师，然后入选了国家海外人才的这个引进项目，就是他的研究方向主要是新型无机纳米材料和无机高分子复合材料的设计、合成以及表征，然后相关的成果也发表了很多在这个顶级的这个期刊上面。因为时间的关系，我就不过多的